Okay, chapter 3, voltage. Very critical chapter. Thus far we've talked about the fundamentals of electricity. We've talked about current. And now we're going to focus our attention to the property of voltage. After completing this chapter, you're going to be able to identify the 6 most common voltage sources, describe 6 different methods of producing electricity, define cell and battery, describe the difference between primary and secondary cells, describe how cells and batteries are rated, identify ways of connecting cells and batteries to increase current or voltage output or both, define voltage rise and voltage drop, identify 2 types of grounds associated with electrical circuits. First of all, there are 6 different voltage sources, period. They include friction, magnetism, chemical, light, heat, and pressure. Friction, I don't know, how many of you are probably the best example of friction would be the Van de Graaff generator? Are any of you familiar with the Van de Graaff generator? I guess it's not a very good example then. Let me give you another example. A thunderstorm. Are you familiar with a thunderstorm? A thunderstorm generates lightning through static electricity and friction of the water and ice molecules inside the thunderstorm because of convective activity. That motion creates enough energy to produce lightning. And if any of you have ever seen a big lightning storm before, it's a tremendous amount of energy. Another example would be me rubbing the chair. When I was rubbing the chair, what was I doing? Friction. Applying friction generated heat, generated electricity. Small amounts. Not a very practical method of generating electricity. This actually is another very important part of lab safety. Not necessarily protecting people, but protecting equipment. In an electronic laboratory, you need to wear ESD protection, electrostatic discharge protection, wrist strap. This prevents you from walking across the floor, building up a static charge, touching a sensitive microchip, and damaging it. You'll learn a lot more about this next quarter, but it's very critical that you understand. That's why you need to be careful when you handle electronic components, that you don't damage them, because you just wearing clothes, the clothes rubbing against yourself and your skin and your t-shirt, whatever, generates static electricity.
I used to work in the Nintendo building in Redwood. And used to fix that, the small DS and all the small things. And we used to wear those things.
Yep. Absolutely. Yep. A lot of companies, you'll get in big trouble if you are in there without wearing protection, because you could damage anything that you touch. So that's one of the reasons that, because you're generating voltage where voltage doesn't belong. Yeah, but the problem with that is that for proper ESD protection, it has a high resistance load in it, so it electrically protects you. If you didn't have that, you're right, if you are leaning up against something and you're grounded, you should be okay to work on something, but it's not a safe thing to do. It's because if you come across an energized circuit, you get electric shock. Magnetism is the most common method of producing electrical energy. This is what we use produced with a generator, an electrical generator. Generator can be powered by steam from nuclear power, coal, water, wind, gasoline, diesel. This is all the way that, this is getting a lot of scrutiny now in the press. What better ways can we come up with turning a generator? This is where, if you've been to eastern Washington lately, they've got the big wind generators, the big windmills. The wind blows, turns it, doesn't matter. It's very safe. It doesn't hurt the environment. It doesn't look real nice, so, hills and hills covered with windmills, but it's not hurting the environment. All it's doing is harnessing the wind. This is another way that we're looking at harnessing tidal power. just the motion of the tides in the ocean. Tidal generating plants to turn the generator to produce electricity. Of course, there's always nuclear. All that nuclear does is produce heat. The heat turns steam, steam turns the turbine, that turns the generator. Of course, gasoline and diesel, with the cost of fuel lately, that's not a real economical way of doing that. And there's also in the Midwest, down in Utah, there's a lot of coal burning plants as well. They burn coal, it heats the water turns to steam turns to steam turbine turns to generator. So this is a way here of looking at a lot of different techniques of being able to turn the generator. If you want to get creative, you can hook up over the gymnasium all the cycles and make that where it generates electricity. Light enough to light a light bulb, maybe. A generator could produce either direct current, where electrons flow in only one direction, or a generator could produce alternating current. This is where electrons flow in one direction, then in the opposite direction. So a generator could be both, either AC or DC. This is the symbol that we use to represent an electric generator. Another method of producing voltage is chemical. This is what we use inside a cell. This is the second most popular method of producing electrical energy. The most popular is using magnetism. Chemical is the second most popular. It consists of two metals, either copper or zinc. This is the fundamental battery, the first battery, if you will. Two dissimilar metals joined together produces a chemical reaction. Many cells can be connected to form a battery. So when we use the term cell, we're only talking about one negative and one positive. This is like a AAA battery, a AA battery, C-size battery, D-size battery. Inside your cell phone you have a battery, which is made up of multiple cells. So you need to be careful how you use the term cell and how you use the term battery. AAAs, AA's, CZs, we call them batteries, but in fact they are single cells. This schematic symbol shows us what one cell looks like. One cell has a negative and a positive. Most companies, their internal standard on schematic diagram will show either 2 or 3, no more than 3 cells connected to represent a battery. If you do see this and you see like 12D written next to it, that means that it's at 12 volts. Multiple cells put together to create a battery. Light is a method used of producing voltage. This is how we produce it through what is known as photovoltaic action. Photovoltaic cell. Solar cell. This is another piece of technology that's being dusted off lately because of energy costs skyrocketing. A single cell can produce a very small voltage. Many cells can be linked to produce a usable voltage and current. Primary use of these is on satellite, camera. The cost is high, but it's declining. If you saw the picture that I showed you earlier today in my presentation from Las Vegas, a company is making thin film photovoltaic cells, which is really going to drive the cost down. So you can cover your whole roof of your house for a very limited cost and produce an abundance of voltage, maybe enough to power your whole home. The traditional solar cells that you've seen pictures of like this, very expensive, very costly. Not real practical for you to use. Another method of producing voltage is heat through the use of what's called a thermocouple. A thermocouple. This is two dissimilar wires twisted together. Voltage is directly proportional to the amount of heat applied. These are typically used as sensors in thermometers and also what's known as a pyrometer. Thermometers and pyrometer. But these are actual temperature probes, typically. But it could be used as a voltage source. It could be used as a voltage source. This is what the schematic symbol of one looks like. Two terminals, and then there's your thermocouple bead. So if you apply temperature to this point right here, the hotter it gets, the more voltage you produce. It's that simple. Pressure, piezoelectric effect. Voltage is small and must be amplified to be useful. This is used in crystal microphones, phonograph pickups, crystal cartridges, and precision oscillators. When you apply pressure to a crystal, this will give us a voltage. This is actually where a lot of sensors, those of you that saw my presentation this morning where I was talking about the Formula One race car with all the sensors that they have in it, a lot of those sensors are pressure. And what it does is it converts pressure into a voltage. The voltage is fed into the computer, and then the car computer makes the determination on how to make adjustments based on what voltage is present. Question?
For example, 3 bottles of milk, or see how much milk is in the pipe. And on the brain, for example, like crystal, drinking much is more voltage. Yes? They see how much is in the...
So they're converting the quantity of milk into weight, the weight into pressure, the pressure into voltage, the voltage controls.
Yeah.
Make sense? I've got a scale at home that I stand on. It's not always a pretty picture. This is what a piezoelectric crystal looks like. The 2 plates and then the crystal. Now, a battery is a combination of 2 or more cells. There's 2 types of batteries I want you to familiarize yourself with. One is the primary cell, and the other is a secondary cell. Primary cells are disposable cells. They're cells that cannot be recharged. The construction of these cells is modeled after what is known as the Leclanche cell or dry cell, also referred to as the carbon zinc cell. Most commonly, probably a lot of you as consumers have gone out and you've bought alkaline cells. What's very popular now is the lithium cell. You could buy, if you've seen Energizer make them, the lithium cells, they last like 7 times longer than an alkaline cell. So if you have a digital camera or a GPS unit or any portable electronic unit, these lithium cells are really, really good.
The lithium cells are usually used for cell phones or
That's lithium ion. Those are designed to be recharged. These are one-time use lithium cells. Yep, designed for one-time use. These lithium cells have been used in a long time in aerospace. I don't know if any of you are familiar with what's called an ELT, Emergency Locate Transmitter. It's like on an airplane. If an airplane crashes, it sends out a beacon that says an airplane's gone down. For years, they've used lithium batteries inside those. No, it's different. This is to send out a beacon to let them know that an airplane has crashed. It's triggered by the impact. It sends off a G meter, and then that triggers the transmitter, and it starts transmitting out. A low jack? Very similar. But in these ELTs for years they've used lithium batteries because manufacturers know lithium works the best in an emergency for the longest amount of time. They're expensive. 4 AA batteries will cost about $8, but they last like 7 times longer. So I do some photography and such. And so like my flash unit, I'll use these lithium batteries. They make them a 9-volt, AA, AAA. Yeah. Although the the TSA just came out with an announcement about limiting lithium batteries on airplanes because of fire hazard. So they're only letting you bring a couple sets of these lithium batteries on board an airplane now. They just changed this in December. In your check bag, I think you're limited still to a couple of them. Just because if it starts a fire, they don't want a big fire, I guess. Kind of interesting. I don't think so, but what I think doesn't count. It's what they think. I think it was stupid that you couldn't bring a lighter on an airplane. What are you going to light on fire on an air? But actually now you can even bring your lighter in your carry-on bag, as long as it's not a butane lighter, but like a Zippo lighter, they let you bring that now. So. Yeah, so I guess they don't want you bringing extra ones. But I think it's a crazy rule, but I think a lot of things are crazy. This is, excuse me, what a cutaway of a cell looks like. And you can see inside. If you've ever had a chance, if you have a carbon zinc battery, it's kind of fun to tear it apart to see how it's put together. You've got the zinc can, carbon rod, electrolyte that is a catalyst of the chemical reaction, produces an abundance of free electrons. It's real simple. Same thing here as a cutaway. I don't expect you to memorize this. It's just kind of fun to look at the inside of how a battery really works. And of course, these are all put together with machines, but it's like batteries are pretty inexpensive when you look at all what's inside, you know. This would be a 9-volt battery, and you see it's made up of multiple cells that are put together internally. Secondary cells are cells that can be recharged. The best example of this would be your car battery, which is a lead-acid battery or wet cell. And lead-acid is still really one of the most popular batteries out there. Another example is the nickel-cadmium cell, or NiCad. And then now we have lithium-ion for like your cell phones or computers. These are all examples of rechargeable batteries. A lot of nickel-cadmium batteries were used in power tools for years, still are.
Like the car battery, you open the hose.
The vent? Yeah.
You can fill them up, right?
Yeah, you need to make sure that you maintain the water level inside, because it's a water-acid solution that is the electrolyte solution. So if that value goes down, then the battery's not going to be able to hold a full charge. So a lot of times I thought my battery has been failing, and I open it up and it's just down on water. You can just add distilled water. Make sure you add distilled water. By adding tap water, it's got chemicals in it and minerals, and it can cause the chemistry to go strange. And this is the inside of a lead-acid cell. And a lead-acid cell has an operating voltage of 2.1 volts. And if you opened up your battery, do you remember how many vents it had? 6. Yeah, 2.1 times 6 equals 12.6. So the nominal operating voltage of a lead-acid car battery is 12.6 volts. Every cell is good for 2.1. The problem is, if you develop a short circuit inside one of these cells, you have to replace the whole battery. For chances are, if you develop an internal short in one of the cells, the other cells are going to fail too.
Yeah, because they're constant.
Yeah. Connecting cells and batteries. Series aiding. Actually, this slide is wrong here. For series aiding, this is correct. But voltage here, total voltage is equal to voltage 1 plus voltage 2 plus voltage 3. This is saying equal, it should be plus. Series opposing, meaning you've got batteries connected frontwards and backwards with each other. Little practical value. Stupid. You would never want to do that. Parallel. This is wrong as well. Here current should be adding. Current total is equal to current 1 plus current 2 plus current 3. Voltage total is equal to voltage 1, voltage 2, voltage 3. The best way of looking at this is with these examples. If I've got 3-volt battery here and I connect it in series with a 3-volt battery, how many volts do I get? 6. What about here? If I have 3 volts connected in series with 3 volts, I get how many volts? 6. But it's connected in parallel with 3 plus 3, which is 6. So what's the advantage of this circuit here over this circuit here at the top? What's that? It would do what? I'm sorry? Okay, but let's assume I just keep it on this load. What's this load going to be able to do now? If this here is just a light bulb, a 6-volt light bulb here and a 6-volt light bulb here, what is the advantage of the bottom circuit as opposed to the top circuit? Yep, these are batteries. Yep. Yeah, that may be correct, but there's another thing that I'm looking for here. Assume that these are all brand new cells. Why would I want to use this, why would I want to use the bottom circuit instead of the top circuit? Yeah, but let's assume it's not going to go bad. You guys know the answer to this. You just don't know you know the answer. It's a simple answer. Want me to give you the answer? No? Because we have to add them in series to increase voltage. The reason that we would do this is this circuit now will last twice as long. So last twice as long. If I have 2 batteries connected in series here and it produces 6 volts, and let's say that this will run this light for 6 hours. When I connect 2 more cells in parallel, the voltage stays the same, but what happens to the available current? It doubles. So now this will last for 12 hours. So if you have a boat, like a sailboat that you anchor and you park and you don't have any other power other than batteries, if you have a recreational vehicle, this all becomes critical. This is why they put batteries in parallel with each other. Voltage stays the same, but the time that it will last will double for the same size cell. A movie that this is illustrated in, it's not necessarily batteries that they're using fuel cells. Remember the story of Apollo 13? They only had so much energy available to get back. So they had to start making decisions. What are we going to use? What are we going to turn off? We can't run the heater. It takes too much energy. We can't do this. We can't do that. We got to keep the parachute warm so when we come through the atmosphere it opens and we don't get killed. So they had to look at every possible circuit and say what is necessary absolutely and what is not. Because they went from this to this. Same voltage, less available current to do the job. Yeah. That's why I personally, like with my car, whenever I replace the battery, you know what I put in? The biggest battery that will fit. Because physically the bigger battery means the more available energy, and in the long run it's just going to operate much more efficiently instead of a small battery.
Is it true that batteries during the cold goes up, like I should show them and stuff, inside will be less.
Yeah, because of the cold temperature, that has an effect on the electrolyte solution of the battery, and that it's not going to operate at optimum performance. I noticed that my car, when I was in Las Vegas for a week, down to the Consumer Electronics Show, when I got back to my car, luckily my son picked me up at the airport, okay? When I got back and started my car in the driveway, it wouldn't start because it was cold and my battery must be getting weak. I charged it up and now it works okay.
Same thing happened to me with the last storm. I got stuck because it was snowing and it was cold, and the battery started to leak and it died.
Yeah.
In the middle of the street, I believe I thought that in the PR came and jumped it and the battery filled, and then it worked.
So you need to replace that battery or you're going to get stuck again.
Yeah.
Yeah, so same thing for me. Maybe we could get two batteries together for cheaper price, huh? Two terms you need to familiarize yourself with: voltage rise and voltage drop. Voltage rise is potential energy or voltage introduced into a circuit. So voltage rise is the energy that we put into the circuit. Voltage drop is the energy given up as electrons encounter resistance in the circuit. So voltage rise, energy we put in; voltage drop is the energy that we're taking out. Finally, two very important terms: ground, earth, and electrical. If any of you do here any hiking or driving your car, if you've ever gone up over Snoqualmie Pass, how do you know that you're going over Snoqualmie Pass, other than a lot of snow this time of year? There's a sign on the side of the road, and what does it say? Snoqualmie Pass elevation 3,600 whatever feet, right? What is that above? Is that the height above North Bend, or is that the height above Seattle, or what is that?
Above sea.
Very good, above sea level. You guys are smart, above sea level. High tide or low tide? Actually, it's above what's called mean sea level, which is the average between high tide and low tide. You know, when they talk about global warming and the sea level rising, that's what they're talking about, is mean sea level rising. So the average rising, and that's a problem. That means really high tide will cause a lot of damage, or a hurricane with a high tide will really cause a lot more devastation than in the past. Okay? So that's the standard that we use for hiking, mean sea level. For electrical, what we use is the earth. What we physically do is we get a rod and we shove the rod into the earth, and we say the earth must be neutral, right? So if we put a rod into it and connect our electrical circuit to it, therefore the circuit must be neutral. That's connected to the earth. So this is what the power company does at the generator. This is what the power company does at the substation. This is what the power company does out at the utility pole. And this is what you have right outside your home, is a ground rod. This is to make sure that when the company, the electric company, sells you voltage, they sell you 120 volts and you get 120 volts. So this acts as a reference for all of our electrical measurements. This is used also to prevent electric shock, because it's a return path, assuming the ground is neutral. Electrical ground is like earth ground, except electrical ground is at a chassis level. This provides a common reference point. This is like on your car. Your car, you connect your black lead to the chassis of the car. That serves as an electrical ground for you. An airplane that's made out of aluminum, they use the fuselage as an electrical ground. You can't do it on a fiberglass boat. You can do it on a ship, but you can't do it on a fiberglass boat. Why? Fiberglass is not a conductor, so you can't. So by using electrical ground like on an automobile, it saves over half the wiring. It saves over half the wiring. If not, you'd have to run 2 wires to every electrical connection. Now on your car, they only have to run 1 wire because the chassis provides the other return path for the circuit current. Does that make sense? Okay. I'm going to talk a lot more about ground in the future. Ground could be the source of a lot of problems in electronic circuits. In summary, we talked about current, the flow of electrons. We talked about voltage, which is electrical pressure. And we talked about the 6 different types of voltage sources: friction, magnetism, chemicals, light, heat, and pressure. We defined the term voltage rise as the energy we put into a circuit. Voltage drop is the energy consumed by the circuit. We talked about ground. There's 2 types of ground. Earth ground that has a rod driven in physically to the ground next to your home, next to your business, out at the utility pole, at the electrical substation. And we also talked about electrical ground. This is where we use the chassis of a vehicle or the hull of a ship or the fuselage of an aircraft to serve as a neutral reference point for all the electrical circuits. Does anybody have any questions over anything that I covered in Chapter 3? Okay, if you don't have any questions off the top of your head, that concludes Chapter 3.